Welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to ESO Paranal Observatory. So, just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010, and I am also part of the staff of an astronomy center at the University of Antofagasta. And regarding my personal hobbies, I am interested in telescope observations and astrophotography. With me is Hector Salas. So, Hector, how are you? Good morning.
Good morning, Fred. Happy to be here. Okay, so my name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany, and I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies. And I've been a member of the team of guys from Paranal Observatory since 2019, when I was doing my master's in Antofagasta. And today I will be the producer, so I will be taking a look at your comments, your questions, and during the tour, at some points Farid will answer them. And yeah, so we are ready to start whenever you want, Farid.
Okay, Hector, thank you very much. So, well, ESO wants to be with you during these virtual visits and bring the astronomy directly to your home or wherever you are. So, please remember you can send your questions or comments during all this streaming. I can imagine you have several questions already. So to do that, you can leave your questions on the Facebook or YouTube comment section. So, or also you can say your name or city, and we will announce it during this tour. So Hector will be ready to receive your questions for later. Okay. Okay. So we are going to start this experience now. So the first step is to help you to understand the place of our visit. So we will begin with some information about the European Saturn Observatory of ESO. So ESO is composed of 16 member states. So now we have a picture there with all the countries, the ESO member states. So the headquarters of ESO are located in Germany, and also Australia is a strategic partner in this case. Chile is the host state and home of all ESO observatories. So from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory and ESO did choose the more suitable areas. So in this case, the mission of ESO is to design, build, and operate astronomical observatories. Why? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, you will see a picture with the three observation sites of ESO in Chile. Here we are. So here is the Shaknantor Plateau, site of the ALMA and APEX radio telescopes. So ESO is part of these places for radioastronomy alongside other international partners. Additionally, south of the Atacama Desert at 2,400 meters, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope, and this one is using a very important instrument, the HARP instrument. So HARPS in this case is an exoplanet hunter. And finally, we have the place of our visit, Paranal Observatory. So this observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on the planet. And in the next few years, we will also have the Extremely Large Telescope, or ELT, the biggest visible light telescope on Earth. Also, the CTA will be an array of telescopes focused on capturing gamma rays. Okay, okay. Now we have a better picture. So now let's travel to the Paranal Observatory. So now you have a virtual trip towards the Paranal Observatory. We are virtually flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where is the ocean? Well, the Pacific Ocean is located below this cloud cover. But why those clouds if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. But above the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. So the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. So now, what other natural barrier we have in this area? Well, if we turn around at about 200 kilometers to the east, we have the Cordillera de los Andes, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So basically, this is one of the best places on Earth for astronomical observations. Okay, so right now we will change the view to have an even closer look to Paranal. So here we are. So as you can see, this is not an ordinary mountain, and now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. So do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. So this observatory is a true oasis. You will see how in one of the driest deserts we have a lot of life and a lot of science. Okay, so right now we are going to change the view again, and we are going to move to the summit of Paranal. Okay, here we are. So in front of us, we have the Very Large Telescope, or VLT, its acronym. So if you see the amount of buildings, four giant domes and other four small and rounded ones, it is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. So here you can find the four unit telescopes, or UTs, each one with a primary mirror of 8.2 meters of diameter, the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So each UT has a name in Mapudungun, the language of the Mapuche culture, natives from central of south of Chile. So here we have Antu, okay? Antu means sun in Mapuche. Cuyen means moon. Melipal, which means four stars, but is This is a reference to the Southern Cross constellation. And this one is Jepun. And this is a reference to the planet Venus as a concept referred to the evening star. So the other telescopes, the closer ones, are the auxiliary telescopes. So they are very special because they are mobile and they can be moved using a rail system up to 30 different positions. They were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short video. So here we have the video. So the technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. Okay, so we are in the telescope platform again. So now you will have the opportunity to visit a telescope, the UT3 Melipal. We can't enter all the telescopes, but don't worry about that because the full ones are identical in size and shape. The only difference are the instruments inside. So you can learn more about the instruments on the ESO website. Okay? So now we are going to enter to UT3 Melipal. Okay, so here we are. What can you see? Well, this is a giant telescope. As you can see, it's very, very big. So we are on the last floor of the telescope at the same height of the main mirror in front of us. So the mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick. I am going to do a close-up. So the mirror was created from a ceramic and flexible material, and the name of this material is Cerodur. So how can we point to the telescope? How can we point this telescope to the sky without breaking it? So we will see it from another angle in order to explain that. So we are going to change the perspective, and we are going to look at this telescope from this level here. So from this position, you will see something different. You will see that the mirror is mounted over this white structure. So this is a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some little gray boxes, these ones, okay? So I am going to show you better. These boxes there are something very special. They are called actuators. They are some kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Otherwise, it could suffer deformations just because of gravity. So those deformations, imperceptible in a first view, could be critical in the result of the observations. Now, how is this working together? We are going to come back to explain that. So we are going to return to this general view. And from this location, we can explain more about how the telescope is receiving light using a short animation. So we have the animation actor. Okay, thank you. So in this case, as you can see, we have to open the doors of the dome. So the light can enter, and the first contact point will be the primary mirror of 8.2 meters. And you will see that the light will be concentrated in the primary mirror and will be reflected to a secondary mirror, and it will be reflected again into a tertiary mirror. So the light can finally go to one of the instruments. And the instruments are represented with those red, blue, and white squares. So we have three different possibilities of instruments. So eventually the light is always going to one of the instruments, and in the instrument is converted into a digital signal. Okay, so this is what happens when the telescope is receiving light. Okay, so you need to understand that eventually we are converting all of this into a digital signal, and this digital signal will be traveling by fiber optics until it reaches the control room. So the astronomers are working from there. Okay. So this is what happens with the telescope. This is how the telescope is receiving light. This is how we are converting this light into a digital signal. So I hope this makes more clear what happens in this big facility. Okay, so in this way, we are finishing the visit to the telescope. So now we are coming back to the main platform. Okay, we are coming back to the Paranal platform, and from this location, I am going to change the view because we are going to another location. We are going to the control room. The control room is the workplace for astronomers and scientists performing the observations. So here you can see this building, right? This building is located on a different level. This is the control building. So this will be the next stop, and I will show you the control building from the opposite side so you can see a different perspective. So basically, from this location, we have the astronomers working at night. But before going to the control building, maybe it's time, Hector, to see if we have some questions. So, Hector, do we have any questions so far?
Okay, Farid, we have several greetings from Andre Popov, from Sue Graven is greeting us from Amsterdam, Pedro Caetano from Minas Gerais in Brazil, Snowy from Denmark, also have Jackie Chan over here. And we have a question here about how do we keep the instruments clean from dust? This is kind of an interesting question. We usually get asked about how do we keep dust from the mirrors, but not from the instruments, so it's slightly different. Can you mention something about that, Farid?
Yeah, sure. Yes, as you said, yeah, the question is actually how to uh, keep all the mirrors clean from dust, because the mirrors are the exposed element, and basically we have two ways to clean the mirror. Well, the first one is an easy way, because once a month, something like that, one or two engineers they need to basically to inclinate the mirror a little bit, and they need to spread a carbon dioxide snow on the mirror. This is something like a foam. Okay, so in this case, this element will remove dust from the mirror, and because the mirror is tilted, is inclinated, the dust and the carbon dioxide will fall to the ground by gravity. So this is an easy way to clean the mirrors, and you need to do that about once a month, and that's enough to keep the mirror basically clean. Okay, but we have another way to clean the mirror, and this is more complex. We need to do this about 2 years, something like that. And this additional cleaning system requires to remove all the mirror from the telescope. So for this purpose, I will show you. I will enter again to the UT3, and I will show you that we have to remove the mirror, as you see here, and the white cell. We have to remove all of this. So when we are removing the mirror from the telescope, we need to transport the mirror to the base camp using a special vehicle, and of course we have to transport the mirror very slowly. Okay, so in the base camp we have another facility So we have to transfer the mirror to that facility, and in that place, we are doing a process that we call recoating. So the recoating is basically to remove the aluminum layer of the mirror. Okay, well, the mirror has a very thin layer of aluminum. So we have to remove the aluminum layer, and we have to put a new layer of aluminum. Okay, so we have to renew this layer. So this process takes around 3 or 4 days. During this time, the telescope is not working. We don't have a replacement. So when the mirror is ready, we have to put the mirror again in the vehicle. We have to transfer the mirror to the telescope platform. We have to lift the mirror, and we have to reinstall the mirror in the telescope. So basically, this is the complex maintenance, of course, because it's very delicate to transfer the mirror and do all the recoating. But you need to understand that this recoating system is the final result is like having a new mirror, because you are actually changing the reflective surface, the aluminum. So that's that's how we are able to keep the mirrors in optimal shape, and that's how we are able to remove the dust, basically.
Yeah, and the mirrors is basically the only part of the instrument that should be exposed to dust. So not the sensible part of the camera, something like that. Okay, we also have more greetings, and we have a comment from Cabrelua saying that he doesn't understand anything in Spanish. So this is the opportunity to remind people that we also do a version of this tour in Spanish. Así que bueno, para Cobreloa y las personas que hablan español, también hacemos este tour en español. Este sábado toca en inglés, en una próxima oportunidad va a tocar en español, así que pueden sintonizarlo en esa nueva oportunidad. And I don't see any more questions, so let's see one. So Chile has a lot of earthquakes. Is there a system in place or some special precaution that we need to have in the observatory?
Yeah. Well, yeah. Chile is a seismic country. So basically, in the underground of the telescope platform, yeah, we have some protections, and they are acting like a cushion, but let's say, in order to protect the telescopes and the mirrors and everything. So we can say basically that, in theory, we can be okay even with an earthquake of 8 magnitude with epicenter in Antofagasta. So you can see that it's pretty strong, and basically, so far, yeah, we have had some earthquakes, but we have never had some important damage in the telescopes. So you can see that it's pretty strong, and this is in consideration of the conditions in the north of Chile. Yeah.
Okay, thank you for it. I think we can continue the tour for now. And
Yeah,
please,
sure.
if anybody have more questions, you can write them in the chat.
Yeah, thank you very much, Hector. So now we are going to continue, and we are going to move to another location. We are going to move to the control building. So I am going to change the perspective, and I will show you the specific place where the astronomers are working at night. So we are going to enter to the control room in order to understand better this place. So here we are. We are in the control room of Paranal. So as you can see, we have several separated workstations. We have workstations for each telescope. In this case, for the UT3 and for UT4. So for example, this one you can see here, it says UT3. So this is basically the workstation for the Melipal telescope, and all operations with Melipal are from here. Okay. In the opposite side, we have the workstation for UT4. So you can see there a sign, it says UT4, and this is basically the workstation for all operations with this telescope only. So now, if we continue walking through this virtual corridor, you will see that we have additional workstations. We have one workstation here for UT1. So all operations with UT1 with and 2 are from here. And if we change again the direction, we can see the workstation for UT2 for Kujen. Okay, so this is another workstation, and you can see that all of them are exactly the same. So this is important because we have all the necessary systems and computers and everything to to work at night. So we are going to access this workstation to take a closer look. So you can see here that we have some computers and we have some people working. So all these people is basically providing the support for the night operations. So, well, overall, we can say that from here we can do the remote control of all the telescopes, instruments, and systems that I was explaining before. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. Each night, we have a telescope operator and an astronomer per telescope. So, for example, let's suppose that this person is the telescope operator and maybe this person is the astronomer. So, the telescope operator, for example, is the person in charge of technical details and the movement, the motion of the telescope. Is like the pilot of the machine. So the ESO astronomer is in charge of to direct the scientific observations and will decide the next steps. So it's someone like the co-pilot. So the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is important because well, this is not like the astronomers are inside of the telescope; they are working from this different location. Okay, so I think this is enough information about the control building. So now we are going to go outside. We are going to come back to the telescope platform again. So now you have a lot more information about the observatory and the people working here. Now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean La Silla, Paranal, and Chajnantor. So here, scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, and also others located in the more distant places in our universe. So now I want to invite you to take a look at the top 10 discoveries from the ESO sites. So please, Hector.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, this was the top 10. It was very, very interesting, of course. But now we have just one more thing. We have something like a bonus track. So let's take a look at this right now. We have another video, okay. Well, this is regarding another news. A team of astronomers was able to capture the first image of a black hole. The Event Horizon Telescope, or EHT, its acronym, it's an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, and it was able to achieve the first direct evidence of a massive black hole. So the picture in this case reveals the black hole in the center of Messier 87, a massive galaxy in a close galaxy cluster in the Virgo constellation. This object is located 55 million of light years from the Earth, and its mass is about 6,500 million times the mass of our Sun. We are looking at the picture right now. Okay, so we hope you liked the top 10, and this was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue. And from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So in this case, we are going to change the view and we are going to provide this picture because as you can see in this case, in this new picture, the sky is almost completely dark with the last traces of light from the twilight, and the moon is below the horizon and the sky is full of stars. So in this case, to begin this journey, I will show you a very popular constellation just above the Antu telescope, the first one on the picture. So I will show you the Orion constellation, this one. This is Orion. So the Orion's constellation in the mythology represents a hunter. So you can recognize this constellation with those three stars. They are somewhat aligned, and they are representing Orion's belt. So, and inside of Orion, we can see another interesting object. This is the Great Orion's Nebula, right here. Okay, so basically, this is the Orion's constellation. It's very popular and it's very easy to recognize. So now we are going to change the position and move to the brightest star in the sky, this one. And this one is called Sirius. Okay, so this star belongs to the Canis Major constellation, and this represents Orion's hunting dog. Okay, so basically, this the constellation of this star is connected in the mythology with Orion. Now, a little bit down, if we go next to Antu, we can see another interesting object. We can see this object right here. This object is basically an open star cluster, and the name of this cluster is Pleiades. These are the Pleiades cluster. This cluster is located in the Taurus constellation. Okay, so this is another very popular astronomical object in the sky. Now, the majority of those objects are visually close to a specific area, a very populated area full of stars. So actually, when we are looking to this area full of stars, as you can see right here, this one, this is one of the Milky Way arms, our galaxy. And our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between Scorpius and Sagittarius constellations. And you can see all this area from this hemisphere, from the southern hemisphere. Okay, so this is one of the arms of the Milky Way. And now we are going to move to another area in the sky to find two spots in the night sky. So I will show you now this area. So if you pay attention here, I will do a close up. This these spots, okay, right here are the Magellanic Clouds. Up there is the large Magellanic Cloud, and down there is the small Magellanic Cloud. They are not actually clouds, they are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. Okay, this name refers to the records of from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were unaware about what a galaxy is. Okay, so this is the reason of why we call these objects the Magellanic Clouds. And another important area right here is the smallest constellation of the sky, the Southern Cross. So I will show you now. This is the Southern Cross, and you can see right here. This is the constellation. This is an easy constellation to find in the sky. Right now, the cross is tilted, okay, as you can see here. The Southern Cross is only visible in this hemisphere and is a good guide to find the South Celestial Pole. And the South Celestial Pole is a projection of the Earth's South Pole. So during the night, the stars appear to revolve around this point. So to find this point, to find the South Celestial Pole, we need to do something. We need to do something with the Southern Cross. So if you pay attention, we have to extend in our imagination the longer stick, this one, the longer stick of the Southern Cross, about 4 times and a half, and in the direction of the longer stick. So basically, if we get the longer stick and we project this like 1, 2, 3, 4 and a half, so something like here, more or less, we have the south celestial pole. So this sun, it also indicates the south cardinal point. So basically, if you look to the horizon, this direction, you are looking at the south cardinal point. Okay, so basically, this is a nice way to uh, to don't get lost if you are in the middle of the desert, for example, with only the stars. Okay. Okay. So this is the conclusion of our visit to Cerro Paranal. So now we are going to return to the platform in the daytime. So we are going to change the view again, and we are going to return to daytime. Okay, and from this location, now we are going to change the direction because we are going down to 2,400 meters in order to visit a very special oasis. So for this purpose, we have to rotate the view like now, and we have to search for the base camp of Paranal. And this is the base camp, okay? So from here, we will visit the residence of Paranal, a place where the ESO staff can stay and rest. So we are going to move, and we are going to show you the base camp. This is the base camp. As you can see, we have a lot of facilities for all the people working here, but we are going to focus on this place. This is the residence, okay? Because the residence is the home of the ESO staff doing their work in the desert, okay? You can see that the main entrance is with this kind of ramp, okay? So we are going to enter now, and we are going to access using this door right here. Okay, so now we are in the residence. And as I told you already, the residence is the home of the ESO staff. Here the workers can enjoy a more humid air. So you can see that they have a swimming pool, some green areas, and also some rest if you compare to the desert and the intense sunlight from the outside. Okay, so you can see that the residence is a very big place. Up there, over there, we have the restaurant, for example, for all the people working in Paranal. Here we have the lobby, here we have the reception. So basically, we have all the necessary facilities and infrastructure for the people working to work, coming to work in Paranal. Okay. Okay, Hector, so I think right now we have more time to answer the final questions because the residence is the final stop of this visit.
Okay, so we have a couple more greetings from Jose Maria, who usually joins these tours, so nice to see him again. Also from Miguel Reyes from Mexico. But we haven't had any more questions, so let me ask you. You mentioned that here's where the people stay when they're working at the observatory. How does that work? Do they work for how many days are they up there in the mountain? Um, can you tell us a bit about that and how many people work in the observatory?
Yeah, of course, we have a lot of people. We have about 200 people working here, and but uh, they are not all of them at the same time in Paranal because we have some people working in Santiago, and some people in Paranal is they are working by shifts. So they are working usually in like 7 by 7 or 8 by 6 shift system. So basically, after your shift ends, you are coming back home, and other person is going to replace you. So we have a lot of people working in different areas. Maybe it's important to say that we have more engineers than astronomers because after all, this is a big and complex machine, and you need a lot of engineers to take care of this machine. But of course, we have some astronomers. probably in any single day in Paranal, you can find about 10 or 12 astronomers.
Okay, thank you for it. And maybe you can tell us about, can people go there in person to the observatory?
Yeah, sure. We have public visits to Paranal and La Silla, but for Paranal specifically, you can do an online booking and you need to go with your own means of transportation. We have available tours on Saturdays at 10 a.m. and 4 p.m. So you need to book in advance because usually we have a lot of people going to the observatory, and the tour usually takes about 2.5 hours, and the travel time from Antofagasta to Paranal is about 1 hour and a half. So you need to plan in advance to get there on time. Okay. But yes, if you can visit the observatory by yourself. Yes.
Yeah, and this is completely free. You just have to sign up in the website first.
Yes. It's free.
Okay, we have a question here from Snowy. How do you choose which part of the sky to study? That is an interesting question. So I will try to answer it. Okay, it
Yeah. Sure.
depends on what do you want to do. So, for instance, there is what they call the survey telescopes that they take pictures of the whole sky and they go mapping the whole sky. And in that case, you can use that type of pictures to focus on a specific area that might be interesting. And certain type of surveys, so usually they take pictures again of the same area. You can look for interesting objects that are changing their brightness or that are moving. That's one thing you can do. The other depends if you're interested in study a very specific thing, like let's say you're interested in studying black holes, then you need to go to the known black holes. So we know there is a black hole in the center of galaxies and in the center of most galaxies. Some of them are active, some of them are not. So you can try to find where these objects that interest you are located. And sometimes it's interesting to study places where there is nothing. For instance, think of the deep images, the deep field, the Hubble deep field images. They point the Hubble telescope to a place where there was nothing of interest just to see what was there, and they put them for a very long time. And this produces images when you can see hundreds of different galaxies. That is a very beautiful images to look at. And this same field has been then observed with many other different telescopes to complement the observations from Hubble. So from what I'm doing right now, I'm working with the Muse extreme deep field. So these are observations taken with the Muse instrument at the UT4 telescope here at Paranal. And they observed the same field that was observed with the Hubble ultra deep field. And in that set of images, I'm looking for a specific type of objects. So I have this whole array of images, and I'm looking at which of the galaxies there are useful for the kind of research that I'm doing. So at the end of the day, it depends on what are you interested. Do you want to do observe a very specific type of phenomenon of objects or not? Whether you want to do something more broad, open, and see what you can find? It's- There's no single answer to decide what are you going to study at this point. And in some cases, it's going to depend on the funding that you have to study things. So I hope that clarifies that a little bit. Okay. Um, we have some more greetings here from Estonia. We have a question from Jose Maria. He's asking us about if you have a picture of a Sagittarius A on his smartphone, how far away would the stars be? That's you will have to calculate it. Getting distances is actually one of the most difficult things to do in astronomy. We can measure velocities uh, fairly well, but measure distances is a bit more tricky. So, how to measure the distance to a group of stars? Well, it depends. So, sometimes you can use trigonometry and use parallax, but that's not available for all type of objects. And sometimes you can, if you have a specific type of stars that you know how bright it should be, you know that this is less bright than that, it's going to be farther away. If it's more brighter, it should be more closer. And we call those type of star standard candles. So yeah, it's not an easy question to answer. Well, at least not in a virtual tool. Okay, I don't see any more questions from our audience. So for my part, I say my goodbyes. It was my pleasure to be here with you today, and I hope we can join us for a different tour. We usually switch between English and Spanish, and between Paranal Observatory and La Silla Observatory. So you need to keep an eye on our ESO social networks to see when the next virtual tour is going to be. Farid?
Yeah, sure. Thank you very much, Hector, for answering the last questions. So yeah, from my side, also I want to thank all the people who was online to um, uh, to stay with us in this virtual experience. And I hope you like this virtual experience, of course. And we have also a survey to receive your comments about this tour. So the link to this survey will appear in the comment section in a few moments. I hope you again. I hope you like this virtual experience. Please stay alert to the ESO social network to know when we will have the next virtual tour. So on behalf of ESO, I want to say thank you very much to all of you for your presence. Okay, so from my side, thank you very much and goodbye.